Hello. So I'm going to start talking about the camera system since it's the first step for any 3D graphics rendering. Typically what you do with uh, cameras is, since we're doing ray tracing, we will want some of coordinate system that we can use to project rays through the screen out to the scene. Let me draw it out. So say we have a camera in some arbitrary position, and we're looking at the origin. Okay. Typically what people do is to put a viewplane in front of it that's oriented in the same orientation as the camera. And this viewplane is way too big. Say there's a viewplane, and this is the eye. This point is the eye, or the viewer. What you do is you want, for each pixel in the, keep in mind this is a 2D plane, it covers the screen. It's the same thing as a screen, so it's a grid of pixels really. So for each pixel you want to shoot the ray through them out and into the 3D world and intersect with some geometry. Then based on the intersection, you shade whatever color that point is to the viewer, then write the color back to whichever pixel this ray intersects. And you do the same for all the pixels on the screen. I'm not going to draw this out. The reason this gives the illusion of 3D is because, if you think about it, the closer the object is, more rays are going to hit the sphere. And if the sphere is moved away from the camera, the distribution, there will be less distribution of rays in the same volume if it's far away from the camera. So as the sphere gets further and further away, it's going to appear smaller when the projection of the sphere on the screen is going to appear smaller. This is why this thing works. This is a 2D illustration of what happens. So you do this for the X dimension of the screen, you do this for Y dimension of the screen, then you'll basically have a camera system that's capable of ray tracing. Alright, but how do we actually achieve that? Now let's go back to Shaded Toy. Remember that the coordinate of the pixel that you're shading right now is given in frac chord. And frac chord is, the unit of frac chord is in pixels. So say your screen, the width of your screen is 200, so it'd be 0 to 200. And if your pixel is right in the middle, then the x coordinate would be 100. So it's in pixels, same in x, same in y. What you want to do, if you, an easy way to go about this is to first remap these values into in between -1 and 1, so that there's no dimensions, say. Because if you normalize it first, the raycasting process will be exactly the same if you're doing on a 200 by 200 screen or 800 by 800 screen. It's just to get rid of that screen resolution dependence, if you will. So first task is to remap it to -1, 1. It's kind of hard to think of a way to do this directly, but we can make it easier by first mapping 0 to 100 to 200 to 0 to 1. So we get a two-step process. Right? If it's 0 to 1, then it's obvious. What you want is the percentage of from 0 to 200. So that would be, let's say, t will be the intermediate value in this range, and x will be the final value in this range. And px will be x in pixels, and this is the raw coordinate, so to speak. So t will first be 100 minus the lower bound divided by 200 minus 0. So it will be whatever value minus the lower bound divided by the upper bound subtracted, the upper bound minus the lower bound. That is because what you're finding is the ratio, the percentage of the value on this number line, how much percentage is it from 0 to 200? How much percentage is from lower bound to upper bound? So when it's turning to t, what you want to do is you can kind of see 0 to 1, the range is 1. The distance between the lower bound and upper bound is 1. And for the next, for a target number space is going to be 2. So first of all, we want to multiply this number by 2, just so we extend the range from 0 to 1 to 0 to 2. Then we can take this range and shift it to the left by subtracting it, by minusing 1. That will move the number line to the left. So it'll be 0 to 2, transforming into -1 to 1. And that's our target number space. So this is how we, not t anymore, there will be x. So this is how we obtain the normalized coordinate for our pixel. And we're going to call this UV in our code. So why don't we just go ahead and do that. It'll be a 2D vector, UV equals frag chord divided by, right. We need, something we need is screen resolution, right? We need to divide by the width of the screen. Well, how do we get something like that? Well, if you click on shader inputs, it will show you all the uniforms to the shader. These are like global variables that are constant during the shader execution. You can think of it that way. So eye resolution is actually something we want. It's the viewport resolution in pixels. We only care about x and y because we only care about the dimensioning x and y. We don't care about z. We don't care about depth, really. So what we're going to do is divide by x and y. Well, what happens when we divide vectors in GLSL? Actually, all the arithmetic operations, if we do them with vectors of the same dimension, they're going to be done per element. So if I do this, the frag chord's x is going to get divided by resolution's x, and frag chord's y is going to get divided by screen resolution's y. And we already learned that the variable that contains the resolution is the eye resolution, so it'll really be this. And remember the equation, we multiply this by 2, then shift it to the left by 1. That is the normalized UV space we want to be in. Just as a sanity check, we want to create, we want to write the color as the x value of the UV. Now keep in mind that UV is currently from -1 to 1, so as UV approaches the right side, it should be brighter and brighter, and if UV is in the middle, that should be black, and black if it's on left. So that's expected. So is Y. So we're good with UVs. So after obtaining the UV, what do we do? I said it would be easier if we do the UV, is because, let's get back to the camera. We're projecting rays through each pixels, right? If our viewport, if our view plane, the screen, is from -1 to 1, that means the width of the view plane and the height of the view plane is going to be 2, right? And if we divide this, it's going to be 1 on each side. Why is that useful? It's useful because it simplifies the calculation of z, the depth of the viewer. This is important because the z distance determines how wide your field of view is, determines how much geometry you're looking at. So if z is really short, then you can see that this angle here is going to be smaller, and therefore the rays that are shooting out are going to be, wider. It's going to capture a wider geometry. A wider amount of geometry. And if z, in contrast, is longer, then that means this angle is going to get bigger and bigger, and it's going to kind of shrink. That therefore captures less geometry in the scene. We can compute explicitly what FOV is given our FOV destination, given our desired FOV, let's say 60 degrees. That's the FOV for human usually, or good enough of an approximation. So let's draw the triangle again. What we really want is for the theta FOV here to be 60 degrees. If we draw the line here to equally divide it, then it's going to be, we want 30 degrees. And remember, each of the halves is going to be 1. And this requires some trigonometry for computing z. So what is z here? Now remember, sine of theta is the opposite over, whatever this is called, but I don't know. But it's this ratio. How do we compute z? Well, z is just 1 over sine 30. What is sine 30 is 1 over 2, so 1 over 2 will be just 2, right? So we've obtained that z should be equal to 2. Given z, given this depth, and given these two, given the dimension of the viewport, and then with that in mind, if we're given any of the coordinate of the pixel, we've already converted that to the normalized range, so it's going to be a fractional number. Something that we can do is just mirror the viewport on the eye, right? On the screen, we already have a UV coordinate on the viewport, if you can imagine that on the screen, UV. And we've mirrored this viewport on the eye that overlaps with the eye. So if we just are given UV with no depth, that means that point is going to lie on this side. If the coordinate of this point is just uv.x, uv.y, and 0, no depth. In order for it to reach wherever the screen pixel is actually at, we need to add the same amount of depth as the camera depth. So it's going to be 2. So this is how we compute the relative vector that goes from the center of the camera to the screen pixel. It will be uv.x, uv.y, 2. This is under the assumption that you're looking straight into z-axis. I guess one more note I should add is we're doing everything in a left-handed system with the coordinate system like this. X is right, Y is up, and Z is forward. Okay, it's going to be a left-hand. I mentioned that it's a left-hand system because it's going to be important now later when we do cross products. So assuming the camera is looking straight into Z, we can easily compute the direction of the screen pixel relative to the center of the camera. Given the direction, we can kind of shoot a ray out to intersect with any geometry. And the way we represent a ray is using the parametric equation, right? So representation of a ray. It is ray origin plus t times ray direction, with t in the range of 0 and infinity. So say you have a point here, this is ray origin and this is RD. Ray direction is usually a unit vector, so that t will be the distance, how far the point is away from the origin. So that's the parametric equation format we're going to use because it's so convenient. T will be, the way we calculate intersection would just be moving the t, right? Ray origin and ray direction will be fixed. Ray direction we've already obtained here actually. It's just this vector normalized. The direction of this vector is the same as ray direction, except the magnitude might not be 1. All we have to do is to normalize it to 1. And we already have ray origin, we can just define some arbitrary point in space. Okay. So let's just do that. Vec 3, ray origin, let's say it's behind the origin by 3 units. And we're going to be looking at some origin. Well, right now it doesn't really matter, I guess. We don't even need ray origin at this point. All we need is ray direction, right? So ray direction is given in this formula. It's just uv.x, uv.y, and 2.0. That's the direction. And how do we know we did it correctly? Well, there's a built-in function. Let's cheat a little bit. There's a built-in functionality inside Shader Toy. We can enable it. It's called cube maps. What it is that, as the name implies, it's a cube of texture maps. So there will be 6 faces in a texture in a cubic texture map. There are 6 faces of textures, and the way you retrieve the pixel that you want to, the way you retrieve any pixels from the texture map is to give it a direction. So you can imagine this cube in 3D with a viewer in the center, and the direction will be shooting out, and whatever texel that it intersects with will be the color that's returned by the texel retrieval function. And how do we know what function to call to get the texture? Well, there is a convenient documentation website called docs.gl. You can go in there and toggle this option. Let's just, we can do GLSL 4.0. This has everything in it, and texture is the one we want. What texture does is that it takes a cube map, takes another direction, and some optional variable that we do not care about, and returns a vec for it. And here we can assume it's the RGBA format of the color, which alpha channel we don't really care about it. As I said, doesn't really have much meaning here. So what we can do is we can just do a fret color, a vec4 constructor with 0.1 as the alpha channel, and we can do texture. You can see the name of the texture here. It's I channel 0, I channel 1, I channel 2. I channel 0. Just type this in. RD is the ray direction. Actually, I have to normalize it. Then I take the RGB value and create a new 3D vector as the color. And now you can see it works. It works a little bit. And by changing the depth, we have different range of FOV. So if Z is further and further away, there's less stuff we can see. And if it's, gets a little closer, the lesser this is, that means the closer the camera is to the viewplane, and the more we can see. The cone that captures all the geometry will be wider, like this. It looks kind of insane, but that proves our camera is correct. Camera implementation is correct. So it's kind of useless right now because the camera can't move around yet. The way you move around a camera is typically you have 2 parameters for your camera. One is the position of the camera, called ray origin, and one is the position of the focus, just call it at. The direction of the camera can be taken by subtracting ray origin from at. So this is the difference vector. That's the Z direction. It's the direction of the camera, like where it's looking at, so to speak. This gets interesting is because a lot of tutorials are telling you to use a rotation matrix to rotate rays, but constructing the matrix itself is kind of cumbersome, and there's really no need to do that. There's a much more straightforward way to do it. We can just utilize the coordinate system. Right. So let's do a little review of the coordinate system. When you write a vector in a 3-element form, what this really means is that this point P, if you start from the origin, you go along x-axis by 1, you go along y by 0, and you go along z by 1, and stop. That's the position of P. So implicitly, P's position is really 1 times x, 0 times y, and 1 times z. However, x, the default x, it's just going to be 1, 0, 0, so when you multiply them, it's going to result in the same vector. However, if we keep the same coordinate, if we keep the same point, and change the coordinate system, so I change the fundamental x and x, y, z axis, and let them stay orthonormal, it will, if we rotate x, y, z in some fashion, then do this multiplication again with the, let's just put a little asterisk here, not asterisk, whatever. So let's denote them to be a different x-axis, but they're still orthonormal, x, y, z. If you do it this way, then P will be the rotated point. It will stay local to the rotated coordinate system. When you compare the default coordinate system and the local coordinate system, the P is going to be the same point relative to your local coordinate system. But if you rotate your local coordinate system, then P is going to rotate as well. So that is a trick we're going to perform. In this case, ray direction is, you can kind of treat it as an offset point from the camera origin. So what we can do is to compute a new coordinate system. It requires a new x, new y, new z, and all three vectors needs to be orthonormal for this to work. So z, as we said, this is the coordinate system we have established. X is right, y is up, and z is forward. Since the camera is looking at the focus, we can obtain z relatively easily. It's just, so cam z is just going to be normalized at minus ray origin. We have z, but we need two more vectors that are orthonormal to z. How do we do that? One way we can do that is to first get some arbitrary vector, and the cross product of cam z and any arbitrary vector will be orthonormal to both of them. What you typically do is to first take the normalize of the result. Then you cross product, or I can just write out the mathematical notation. You cross product, this is the global y-axis, you cross product it with the z axis in the camera. If you take out your hand, take your left hand because it's a left-hand system, you point toward y and you curl into z, the thumb will be pointing at the x-axis that's orthonormal to both axes. So that's why it works. And we can compute y by just doing a cross product between x and y. And again, if you take out your left hand, the way you obtain y is you cross cam z and cam x. The order of cross product matters. If you do it the opposite way, then it's going to have a totally opposite vector. So be careful the order you multiply. So cam z cross cam x. And given these three vectors, they make a local coordinate system for the camera. And in order for the direction to be be rotated the same amount as the camera, whichever orientation you're at, you want to multiply each component of the direction with each axis. Intuitively, you can think of it as move along. Okay, so the camera is looking at this way. This is y, this is z, this is x. So ray direction assumes that it's at a default coordinate system. So, but we don't know where x, y, z is at. So what you do is take out each element of ray direction, multiply by the axis. Whatever axis it is, it's going to move along x this way, move along y this way. It's going to be going down, and it moves along z this way, right? Then the result is going to be, it's going to stay relative to the coordinate system, no matter how much it rotates, orients. The only downside is when this coordinate system breaks when the camera is pointing directly up, because this thing will be cross-producting itself and the result will be zero. And you cannot normalize a zero vector. It gives you nothing. So you have to kind of do that. But in all my renders, I don't really need to look directly up, so I just keep this. It usually works. So why don't we go ahead and do that? Let's set a camera point origin. So ray origin is equal to, let's say, origin. You go to origin, then step back by 3 units, and you stare at the origin. Camera z is, as I've said, it's the normalized at versus ray origin. Cam x is normalized cross product global y-axis and cam Z. And one trick you can do, this is not really a trick, it's the rule of cross product. If cam Z and cam X are both orthogonal and they're both of unit length, then the cross product of them two is guaranteed to also be unit length. So there is no need to normalize them. That is because the magnitude of the cross product is the multiplication among the magnitude of vector 1, the magnitude of vector 2, and the sine of the angle that's between them, which in this case is always going to be 1. So we can just safely cross product without a need to normalize, which I think is kind of neat. It's a neat discovery. Ray direction, as I said, will multiply each element in ray direction with each of the orthonormal axes in the local system. So what we do is we're still going to have a normalized ray direction, but uv.x will now be multiplied with cam.x, uv.y with cam.y, and 2.0 is going to multiply with cam.z, and that's the new ray direction we have. Doesn't really change. Well, it will change when we change the focus of the camera. Let's say we look to the right a little bit. So 1, 2, 3, 5. That's pretty good. However, there's a problem with the camera that we have right now. The problem is kind of subtle in this case, but if you compare the reference image in the I channel and the image we're rendering, there is a difference in scale. You can kind of feel that the image is stretched in a certain dimension. Well, that is because the screen we're rendering to is not equal. It doesn't have equal width and height. What that would mean is that since we're treating the viewport in space as equal sides, so we're treating it as a perfect square, but it's actually a rectangle. That means rays will be distributed unequally in one of the dimensions, and that will result into a stretched image. The solution is quite simple. One of the hints is you can just stretch something else to cancel out, stretch it in the opposite direction to cancel out the stretching effect we're having. Right? If you think about it, you can solve it very easily. So the image is stretching, use some counter stretching in some parameter, and we can simply get rid of this effect. I'll leave it as exercise, and I will give you the solution in the next video. Don't try to look it up. Try to think about it. Don't look it up right away. Give it some time, and you should be able to come up with a solution easy enough. So this is the camera. I guess one last thing I could add is center origin. One more parameter in shader toy is time. This is how many seconds the shader has been played. It's displayed right here. Something you can do, since a circle is basically, the point in a circle is a combination of sine and cosine. What we can do is do sine I time. We want to rotate around the y-axis so we don't rotate up. We're more like walking around on the equal on the same xz plane. So we don't really want to touch the y-axis. But if we change up x and z axes, we'll be rotating the camera. That's pretty neat. This way we can test that the ray origin works, since in our process of retrieving the color we don't really have ray origin in it. Now we're testing that the ray origin is also working correctly. So far this is known as a simple pinhole camera. It's nowhere near realistic. So you don't have any fancy effect like depth of field or bloom that comes out naturally, but it's good enough for just 3D graphics. So that's it. Try to think about the aspect ratio problem, like the unnatural stretching of the image. How do you fix that? All right, that's it. Thank you.